In this video, we're going to decide how to identify whether a reaction is a redox reaction or not. To do that, we'll also review how to assign oxidation states, and then we'll decide how to identify the thing being oxidized or reduced in a redox reaction. So let's begin with this question here. We have a chemical reaction in front of us, rather complicated looking. Iodide ions are reacting with permanganate ions and water to produce iodine, manganese dioxide, and hydroxide ions. Is this a redox reaction? Well, to decide that, let's start by putting in oxidation states. We remember the rules for assigning oxidation states. The first rule said that if you see an element by itself, a pure element, then its oxidation state is 0. In this reaction, we see on the right I2, 3 moles of I2. The coefficient in front doesn't matter. The formula is I2, and I2 is just an element. So the iodines in I2, we would say, have oxidation states of 0. So let's just put a 0 above them. The second rule for assigning oxidation states said that if you see a monoatomic ion, an atom by itself with a charge beside it, its oxidation state is the same as its charge. So on this reaction, the very first thing has I minus. So I minus is a monoatomic ion. Its charge is -1, or 1 minus rather. So its oxidation state would be -1. So we've got 2 of the oxidation states. The third rule said that if you see oxygens in a compound, oxygens are almost always -2 for oxidation states. So we see lots of oxygens here. In permanganates, we can say that the O's there are -2. In water, there's also -2 above the oxygens. In MnO2, we have a -2, and in hydroxide, we have -2. So the oxygens are always -2, almost always -2, when they're in compounds. Now, the fourth rule said hydrogens in compounds are almost always +1. Now let's just take a look here at water. We see H2O, and if we put a +1 above the hydrogens, we notice that there's 2 hydrogens, so that gives me 2 positives, and there's 1 O, and it's -2, and so we notice that the sum of its oxidation states is 0, and that's true because the water molecule here has no charge. It's just H2O. On the right, we see an OH-. It has a hydrogen with an oxidation state of +1, and we notice there that the O is -2 and the H is +1, and when we add those together, we get a charge of -1, and a total of -1. That total matches the charge that we see here beside the hydroxide. The sum of the oxidation states in a compound has to equal the charge beside it. So in OH-, the sum had to equal -1. In water, that sum had to be 0 because water is neutral. On the left, we still have this MnO4-. We notice that its charge is minus, so the sum of its oxidation states would be -1. It has 4 oxygens, and the oxygens are each -2. So 4 times -2, there's a total of -8 from the oxygens. So what must be the oxidation state on manganese, the Mn? Well, if we've got -8 from the oxygens, and the entire thing has a charge of -1, then that manganese must be positive, and +7. Now on the right, the manganese there is bonded to 2 oxygens, and MnO2 is neutral. There's no charge written beside it. So if there's 2 O's, and that would give me a total of -4, 2 times -2 is -4, then that one manganese must be +4 to give me a total charge of 0. Now notice that a couple of the things in this reaction, a couple of the elements, have changed their oxidation states. The iodides started at -1 on the left, and on the right they finished at 0. So let me just draw an arrow from here to here. The iodides began at -1 and finished at 0. The manganese began at +7 and finished at +4. The fact that we see changing oxidation states, that is enough to decide whether or not this reaction is redox, and the answer is yes. This is a redox reaction. It's a reaction involving reduction and oxidation, redox. Now, you remember Leo the lion says grr. So, losing electrons is oxidation, gaining electrons is reduction. Let's take a look to see if we can figure out what was losing electrons and what was gaining electrons. We'll see if we can figure out what was oxidized and what was reduced in this reaction. I minus began at -1 and finished at 0. The iodides on the right have an oxidation state of 0. To go from -1 to 0, if you think of a number line, -1 to 0, you went up in oxidation state. So why would you go up in oxidation state? Well, the answer is you're losing negatives. If you take away negatives, your charge, your oxidation state, gets larger. So since electrons are negatives, the fact that you went from -1 up to 0 means that you lost 1 electron. And losing electrons, Leo the lion, is oxidation. So we would say that the iodides are being oxidized in this reaction. The I minus here is being oxidized. Now that means something else has to be reduced. There has to be reduction. If there's oxidation in a reaction, there must also be reduction, and that's why they're called redox reactions, because reduction and oxidation are happening. Now if we look at the manganese, the MNs, we notice that they began with +7 oxidation state and they finished at +4. So to go from +7 to +4 on my number line, I'm going to have to make it longer here. 1, 2, 3, there's 4, 5, 6, 7. To go from 7 down to 4 would mean that you had gained 3 negatives, right? Negatives are going to bring you down on the number line. 7 down to 4 means you gained 3 negatives. So we had gained 3 electrons, E minus. Gaining electrons is reduction. So we see an oxidation reaction, the iodides become iodine. We see a reduction reaction, the permanganate is becoming MnO2. Now, we could say that permanganate is being reduced, or more specifically, the manganese in permanganate is being reduced. So there's an overview. This reaction was redox because we saw a change in oxidation states. We could also tell from those changing oxidation states what was losing and what was gaining electrons, and therefore where was the oxidation and where was the reduction reactions. Alright, let's look at one more example, and this one will be a little bit faster. Here's another complicated looking reaction. Is it a redox reaction? Well, let's very quickly assign oxidation states. We see several monoatomic ions, so that should go fast. The Fe2+ must have an oxidation state of +2. H+ must have an oxidation state of +1. On the right, we see Fe3+, it must have an oxidation state of +3. And we see chromiums, which have 3+, and so they also are +3. We see oxygens, they're -2, they're in compounds, so -2. And then on the right, the hydrogens there are +1. And on the left, we have this chromiums. Now this one we'll have to take just a moment to calculate. The whole thing here, Cr2O7, has a charge of 2-. There's 7 oxygens, so 7 times -2, the oxygen's oxidation state, plus 2, there's 2 chromiums, 2 times something, whatever chromium's oxidation state is, has to be -2 the charge on the ion. So one more time, 7, because there's 7 oxygens, times -2, because that's oxygen's oxidation state, that gives me -14, plus 2 times something has to be -2. Now the -2 at the end is because the dichromate had a total charge of -2. Well, -14 plus 12 would equal -2. So 2 times something had to give me 12, and that something is +6. So the chromiums in dichromate are +6 oxidation states. Now, as soon as you noticed that the irons had changed from +2 to +3, that was all you needed to see to decide that, yes, this is redox. It's redox reaction because it has a changing oxidation states. As soon as we saw the Fe2+ become Fe3+, that's all I needed to see to decide that there was changing oxidation states. Now let's be more specific. The Fe2+ becomes Fe3+, and that means the oxidation state went up. It went from 2 to 3. If it goes up, you are losing electrons. Lose 1 electron to go from +2 to +3. And Leo means losing electrons, is oxidation. That means there has to be reduction as well, and we notice that the chromiums began with +6 oxidation state and they finished with +3. So to go from +6 to +3 means that you're gaining, and this is a bit of a coincidence because I think this is the same as the previous example, gaining 3 electrons. And gaining electrons, Leo says gaining electrons is reduction. Therefore, the Fe2+ is being oxidized while the dichromate is being reduced. Now, we're going to learn in class a couple new terms, the oxidizing agent and the reducing agent. The oxidizing agent is the substance which causes, that's why it's called an agent, it causes something else to be oxidized. Well, in this reaction, the Fe2+ is becoming oxidized, so why is that? What's causing it to become oxidized? Well, the answer is the dichromate. Dichromate is causing the Fe2+ to become oxidized. Therefore, we notice that the thing that gets reduced, the dichromate, is the oxidizing agent. The substance which gets reduced is the oxidizing agent. Similarly, the Fe2+, which is being oxidized, is causing dichromate to become reduced. So the Fe2+ is the reducing agent. Misspeaking here because it's late in the evening. So Fe2+, the thing that gets oxidized is your reducing agent. The thing that gets reduced is your oxidizing agent. So once you've identified what's being oxidized, then you know right away that that substance is the reducing agent. When you identify what's being reduced, you've also identified the oxidizing agent. Alright, so those are more key vocabulary terms in this unit on electrochemistry.